Hi, my name is Ray Benton. You can call me Kim Ray. I'm going to do a quick tutorial on the atom. What is an atom? The atom is the basic unit of matter. Most things that you can see, even things you can't see. Gases, microscopic stuff. Components of the atom. The atom is composed of a dense central nucleus surrounded by a cloud of negatively charged electrons. The atomic nucleus contains a mix of positively charged protons and electrically neutral neutrons. The electrons of the atom are located outside the nucleus of the atom. The mass of the atom arises from the protons and the neutrons, the combination of them together, with an insignificant amount of mass coming from the electrons. Number of protons in an atom designates its atomic number. Each atom has an isotope due to the addition or removal of neutrons. An atom can be changed by removing protons from it, but then it becomes a whole new atom. The organization of a hydrogen atom is as shown below. This is the simplest example that you can probably find, and it was initially proposed by Niels Bohr. And it's known as the Niels Bohr theory of the atom. In the hydrogen atom, what you see is a sphere, and in the center of that sphere, you find a proton. And on the outside of the sphere, you find a single electron. The mass of the hydrogen atom is 1. As we said earlier, the protons plus the neutrons equals the mass. Well, if we have 1 proton and 0 neutrons, the mass has to be 1. The one thing we can say about hydrogen while we're here is that there are isotopes of hydrogen. So if I was to add in more neutrons, I could have either deuterium or tritium, which are the two most common ones we're familiar with. Deuterium being one that we associate with nuclear power and heavy water, or even nuclear bombs or other things. A more complicated example of a Niels Bohr's model would be that of carbon. Carbon has this central nucleus, and within that central nucleus, what you would find is 6 protons and 6 neutrons. In this picture, as you can see, the red dots are the protons and the white dots are the neutrons. Outside of that central nucleus, we have 2 electrons. And then we have another sphere outside of that, which has 4 electrons. And if you look at the periodic chart, the mass for carbon is 12, which is 6 protons and 6 neutrons. And in these outer shells is the remainder of the stuff, which we call electrons. There are several isotopes of carbon. There's C12, C13, and C14, and all of these have their significant contributions in science. Looking at a periodic chart, I wanted to point out quickly that the periodic chart has its elements in very organized fashion. If you look at it, it's across from here. Hydrogen's on one side, helium's on the other. Everything underneath helium are considered inert, actually. That means these are very difficult to get to react with other molecules. If you move back one row, over here, we're starting with fluorine, chlorine, bromine, iodine, and actinium. The ones that we're mainly familiar with is basically iodine, bromine, chlorine, and fluorine. These are very reactive, always looking for an electron. And if we look on the other side over here, the lithium, sodium, potassium, rubidium, cesium, all these guys, and the ones that we're probably most familiar with is potassium, sodium, and lithium, these guys are looking to get rid of an electron. The electronegativity in the periodic table is known to increase from left to right and top to bottom. And what does that electronegativity mean? It's the ability to attract electrons. There are several types of bonds. There are covalent bonds, ionic bonds, polar covalent bonds, hydrogen bonding, and London dispersion forces. And the reason I point all of these out is because all of these bonds have some form of an atom's electrons involved in them. Particularly in covalent bonds, these are bonds that are shared equally or close to equally between two different atoms, or even two of the same atoms. Ionic bonds, in the case of something say such as sodium chloride, the ions would be the sodium with a plus and the chlorine with a minus. And the reason that sodium now has a plus is because, as I said, it's on the left side of the periodic chart, really willing to give up an electron. And the chlorine on the right side of the periodic chart, highly electronegative, really wanting to take on an electron. It does that, the sodium gets a positive and the chlorine gets a negative. You put the two together, you get that nice sodium chloride or salt. There are polar covalent bonds, hydrogen bonding, and London dispersion forces. And why all of this bonding business? Stability, stability, stability. So if you are pursuing chemistry, biology, or some other form of science which requires chemistry, I would recommend that you give me drop me an email. You can Raymond_Benton_1 @yahoo.com, or you can call me at 415-236-2699. That's 415-236-2699, and someone will get back to you as soon as possible. I don't want to leave you with this Bohr model only of a theory for how atoms are described. A better, more up-to-date model would be to look up something from Schrodinger, which is the Schrodinger equation, which is a mathematical equation derived derived to allow one to describe the actual orbital of atoms, where it is most likely to find an electron in its orbits around a particular atom. And once you do that, what you'll find is that the Schrodinger equation has a much better description in terms of the actual shape of these orbitals. The circular orbital is correct for s orbitals, so Niels Bohr was right on with that. But once he went past the s orbitals and he started to get into p orbitals and d orbitals, which may be associated with d orbitals with metals or something. And if you're doing you're new to organic chemistry or inorganic chemistry, d orbitals probably won't be a big concern of yours, but the s orbitals and the p orbitals will be, especially the lower ones. Thank you so much for listening to my tutorial, and please see my further explanation of Schrodinger's way of describing the atom.